So I'll now go through some of the design steps. To get one of these structures in place, I'll go through a whole range of design steps. They're fairly extensive, and I've got some examples of most of them along the way as well. Each of the steps may require input by the proponent for the project. Some of the steps, that's what's required. Other steps require a specialised coastal engineer to give a bit of input, and some of them are a bit of a joint decision between the project proponent and a coastal engineer. So the first step I'd say is, what is the objective of the structure? It sounds pretty obvious, but at least write down or document why you want to build it, other than just some residents screaming that they want coastal protection. It needs to be at least a bit of a justification. So what is it that's being protected? So assets or beach amenity, and consider other issues such as public safety and how you might remove the works down the track. Second step is to consider the design life of the structure, being very wary of the example I showed of Stockton, where often that's far exceeded, but nevertheless, at least consider what the design life you intend to have for the structure is, and realise that may well be extended far beyond what you originally intended. Also consider or document the consequences of damage to the structure or the assets that are being protected. So again, you need to at least justify in some sense, whether monetary or through a subjective measure, what it is you're trying to protect. So generally estimate the value. Monetary is probably the way that most decisions are made based on economics. Not always though, can be subjective reasons. An example, a very early geotube structure we were involved with was to protect, it was Lake Victoria in western New South Wales, and it was actually to protect Aboriginal burial grounds that were being eroded by processes. So pretty much impossible to put a monetary value on that, but it had a strong value to the community, so that was a justification for taking the works on. So sometimes, and something like beach amenity, again, not as easy to put a dollar value on, but you can still put a subjective value that it's important to the community. Assess the potential for repairs or maintenance. No structure is completely maintenance free, but at least work out whether you're prepared to do some maintenance or you want to minimise the maintenance. So make some judgment upon how much maintenance you're prepared to do. Then assess the risk and allocate a design event. I'll give you some examples of that, but you've got to accept what event you wanted to design for, and that's somewhat determined by the life of the project and how much certainty you want in the project. Also undertake or acquire a survey of land areas. They often already exist, but the gold standard to do it at the start of a project is to get a specific survey done by a registered surveyor, and that covers all your bases really nicely, but often not done, but at least have some sort of survey of the land areas for what you're proposing to do. I mentioned about allocating a design event. There's probably people with a range of backgrounds in here, and again, you've recently had Brisbane floods, so recurrence intervals are on everybody's mind around here. But an example of how to come up with a design event, most people are just fixated with using a 1 in 100 year recurrence interval design event, and if you look at this graph here, we've got typical recurrence interval starting from 10 going all the way out to 10,000 years. We can design something to withstand a 1 in 10,000 year design event, but the cost to build that structure keeps going up and up and up. So we can reduce our risk, but we're having to build a more and more expensive structure. Equally, this is our risk curve. If we design for a 1 in 10,000 year event, our risk is very low, but we have a very high construction cost. Conversely, we design for a 10-year event, our construction cost is low, we only need a pretty small structure, but our risk becomes very high because there's a pretty high chance it's going to be damaged or fail. The hypothetical reason why 100 year has often been written into a lot of the standards is that when you add these two curves together, they tend to, you get this total cost curve, and in theory it can optimise itself at about a 1 in 100 year event. So that's the theory why a lot of planning codes and standards for reasonably long-term structures all end up adopting a 1 in 100 year event as its design event, but just realise there's all sorts of problems in that as well. Just some examples of design events to be used for any sort of structures. Probably the more correct way, if you're into your statistics or a practicing engineer, what we call encounter probability is probably the most correct way of doing it, but that gets pretty involved. Some other standards, the Building Code of Australia for private houses are we normally design those for a 1 in 500 year event for wind loading, a 100 year event for water entry. There's an Australian standard for design of maritime structures, which technically doesn't cover breakwaters, but for general infrastructure in a marine environment, it talks about, depending on how you interpret, between a 500 and 1,000 year event you should be designing for a long life structure. Most flood policies in America and Australia generally allow about a 100-year recurrence interval to be used, plus a freeboard on top of that. It's worth noting that the main coastal defences in the Netherlands are designed for a 1 in 10,000 year event. And similarly, we have done some work for these apply to sort of private housing, but we did do some work once for a new emergency hospital that was going to be on the waterfront. And there's not really proper standards for that, but it got pushed up to being designed for a 1 in 10,000 year event. And most of the guidance on that, again, it's in the news right now with nuclear reactors. The majority of the guidance for how do you arrive at a 10,000 year event comes out of a lot of the nuclear power stations in Europe are all designed for that sort of water level. So most of the studies and engineering on that has all come out of nuclear power station design. And obviously the example that's been in the news recently was originated in the 60s when they probably didn't have that sort of information as readily available as they do now. So on to another design step. Collect or acquire bathymetry data. That's a bit harder to get. It's often obtained from bathymetric charts, but the information on those is often from very old surveys. Certainly even today, some of the mid-north coast of New South Wales, the bathymetric charts, if you read the fine print, were acquired about 1850s or thereabouts, believe it or not. So there's some very old bathymetric chart data, and when you read the fine print, so best practice would be to go out and collect it specifically for your project. Usually there's not enough funds to do that, but certainly that's best practice. Another really common mistake I see, bathymetric charts use a different datum to land surveys, so they normally work to chart datum, the part of the profile underwater, whereas the land surveys usually work to AHD, Australian height datum. So that's a very common mistake that I've seen during projects, and worth noting that. When you've got all the profiles and levels, assess an offshore design water level. Normally it's taken from analysis of tide gauge records or numerical modelling. There's existing analyses for most mainland Australian locations that you can usually draw upon, but some sites you might need some specific studies. I've got some examples of that. So work out what the extreme water level you need to design for is, and then also an offshore design wave height. Again, usually undertaken from measured data of wave buoys, but sometimes some numerical modelling is needed as well. Here's a few examples from places around Australia. This is just an extreme water level based on tide gauges. It pretty much applies from the open coast of Fraser Island all the way to Hobart. Most of these curves do. And here's a few examples. The top curve is extreme recurrence interval for Sydney based on about 100 years of data at Fort Denison. And what it says is that on a tide gauge, the 100-year level for Fort Denison is around about 1.5 metres AHD. The bottom curve here is actually Fremantle in Western Australia, so a little bit lower, but you can still, there's again 100 years of data. We can work out what the 100-year level is on the tide gauge pretty easily. The thick curve is Hobart. So just some examples of tide gauges around Australia. So Hobart sort of sits in between Sydney and Fremantle. Certainly other places, Northern Australia has far higher tide ranges as you'd expect, North Queensland and north of Western Australia, but from Fraser Island south on the east coast, you're in this range really. Onto waves, there's a network of wave buoys covering most of Australia. Again, you've got to get some sort of offshore wave height for design of the structures if they're on the open coast. I've put just the most extreme one in the country on here. This is off the west coast of Tasmania called Cape Sorel, and it's been in operation for around about 15 years. And as you'd expect, it gets the biggest waves in Australia. So the 100-year significant wave height on that Cape Sorel buoy is around about 13 metres. And so the maximum wave heights there can be up to double that. So it's had the biggest wave events recorded on Australian buoys. There was an event in 1985, it was about 13.5 metre significant wave height. Most of the rest of the east coast of Australia is more down, represented by, say, Eden, New South Wales buoy, which is the offshore 100-year height is around about 8 metres. And then you have to bring those waves to the shore. So that's what they are in the deep ocean, but then those waves will transform through a range of processes and break, and then they'll be smaller by the time they hit the shore. Here's a few examples from a whole lot of buoys up and down the east coast of Australia, and this is basically average recurrence interval from 1 year out to 100 and what we expect the significant wave height to be for a range. Now, the closest one to here is Brisbane, which is actually, it's called Brisbane, but it's outside Stradbroke Island, out off Point Lookout. And the 100-year offshore wave height for Brisbane, the orange lines, around about 8 metres. So that's the significant wave height. You get the maximum waves in a given storm can be up to twice that. So that's the sort of offshore conditions you need to design for anywhere up and down the east coast, south of, say, Fraser Island. But then you have to bring those waves to the shore. So in order to bring those waves from the deep ocean into your structure, there's a few other steps that you need to do. One of them, important ones, is estimate the likely range of sand that's going to front your structure. So if you're building a structure on a sandy beach or in front of a dune, the sand in front of that structure is going to move up and down with the storm cyclone. It's going to erode. It's in reality, as a coastal engineer, that's probably the most difficult step in the whole process, is estimating how much you believe that sand is going to scour in front of the structure. There's a few ways you can do it. Photogrammetry is one way, which is historical aerial photos to look at the change from that. Historical site surveys, if they exist, but they're actually quite rare. It's rare that people have gone out and surveyed probably the Gold Coast, some of the beaches of the Gold Coast, probably the only place that's been done, certainly in Queensland regularly. Numerical modelling, which is computer-based beach erosion models to try and estimate it, or rules of thumb or judgment. It's often accepted East Coast, open coast, we often design for the sand to scour to -1 metres AHD. It's just a rule of thumb, but it's something at least, and it's usually more conservative than the other methods. So nevertheless, whatever method you use, there's a big element of judgment in this step here, and it's quite important because it determines how deep the water is in front of the structure, which determines how big the waves are that can actually hit your structure. So once you've done all the steps before it, it's transforming the design waves to the structure. So you might have an 8 metre wave out in the deep ocean and a 1.5 metre AHD water level, but the waves are not going to be that big by the time they hit your structure, and I'll show you some examples of that soon. For open coast, there's a few ways of transforming the waves to the structure. I've called them decreasing order of complexity. So the gold standard, the best practice is to do two-dimensional numerical wave modelling. The most commonly used model is called SWAN, preferably supplemented by measurements at the site. Again, rarely done, but that would be best practice to do this method. If there's not enough resources or time to do that, you can do one-dimensional wave modelling, which I've got some examples of. The most commonly used models, Dalydine and Dalrymple. Less complex, again, is just to do depth-limited wave height calculations at the structure. So the most traditional rule is that the wave height can be about 80% of the water depth. So if you work out the water depth at the structure, so if you end up with a metre of water at your structure, you have a 0.8 metre wave potentially can hit your structure. That's the most simple method, but that can be a bit misused because people don't consider wave setup in those calculations sometimes, and you need a lot of care as to what level you assume the sand bed to be as well. But that's the most simple method. This is the more complex method. So some examples of the more complex method. This is a proper, what we call SWAN wave modelling, where in this particular case we could have waves of between 8 and 10 metres out in the deep ocean out here, and the swell lines, this is like wave crests, and they propagate up into a bay like here. And obviously they're much smaller up here than they are out in the deep ocean. This is when we run that through a computer model. In this example, the model's SWAN. The red are the really big waves, and it grades down to blue for smaller waves. So we have a boundary across here, and we start with about 8 metre waves coming through here. And as they move up into the bay, those waves spread out and they refract and diffract into this bay here. So by the time we get up into the bay here, we've possibly got only 2 metre waves, and we may have about 4 metre waves at this particular beach here, but we've started with 8 metre waves there. So this is an example of the model output. It all looks nice and pretty as well, but to get a design wave height at a given location, we have to go a bit more black and white than that. So even though the other graphics look really pretty and look impressive, this is probably for a raw engineering calculation, this is more what we need. So for a range of offshore wave directions, realise it's very direction sensitive. So this particular site, we've got wave directions going all the way from east out to west, and southerly waves are here. And obviously that site looks pretty open to the south, if you saw. So this is really a coefficient that tells us what the percent of wave height is compared with what it is in the deep ocean. And obviously it's 0 here and it's 80% up the top here. So for this particular site, obviously it's quite open to the south, so the coefficient's about 75% if the waves are from the south or the south-southeast. If they come from the straight west, the coefficient's about 10%. So it means if you start with a 10 metre wave offshore, you've got a 1 metre wave at the site if it's coming from the west, but if it's coming from the south, you've got about an 8 metre wave still just offshore from the structure. So you've got to put all that modelling together to come up with a wave that's actually going to hit your structure. As well, that's open ocean swell waves, but also a lot of sites aren't exposed to that at all. An example might be some of the shores of Moreton Bay, where you're only exposed to local wind waves, which is just the wind blowing over the water. So the ocean swells can't really get in there with any real size. So here's an example of how we'd work out the wind wave climate to design for at any given site. So if we want to pick a site here, we consider all the potential fetches that the wind can blow across the water. And the most common engineering way to then come up with a wind speed is that there's a pretty well sorted out design standard for design of wind load on buildings. So normally we just use the design curve for wind speed for buildings and make some modifications to that based on duration, and we can come up with an extreme wind wave climate at any point along here. So the next step is to estimate the local water level and the water depth at the structure. So we've already worked out our wave conditions and we've already made an estimate of the scour in front of the structure, but the local water level includes wave setup. And if you're not familiar with the term, I've got an example of it soon, but because of the waves coming in, the water level in the surf zone actually rises up compared with what it would be on a tide gauge. And that water level is very important because it determines what the maximum wave height is that can actually impact on our structure. So once we worked out a local water level, we then work out the design wave condition at the structure. Even though it may well be 8 or 10 metre waves out in the deep ocean, by the time they reach our structure, they're going to be much smaller in height, and they may well be, for a geotextile structure, we're hoping they're in the range of less than 1.5 metres to make the structure work. It's based on the offshore waves and the transformation of the waves and the scour level we assume at the structure as well. When we put all those together, we work out the stability of the containers in a proposed structure, which I've got some examples of desktop methods. And the desktop methods are suitable for reasonably low risk or for small wave climate conditions. If there's a lot of risk in the project or reasonably big waves at the limit of the structures, it's certainly recommended, as it is with rock structures, that physical modelling is undertaken. So here's a bit of an example, putting a lot of those previous steps together to come up with a design condition for a structure. So this particular, it's a distorted scale, so the vertical scale is stretched relative to the horizontal, so you can see what's going on. This is our proposed geotextile structure on the foreshore in front of a sand dune. The profile offshore is this black line here, so we're going out into about 15 metres of water. For this example, we're starting with about a 6 metre wave offshore, so the blue is our wave height. So we have a 6 metre wave coming in, and this is what's called a one line or one-dimensional wave model. So we start with a 6 metre wave. It actually, probably everyone here has swum in the surf or seen the beach at some time. As the waves come in, they actually usually rise a little bit in height before they break. So we've all had a swim in the surf and seen that. So this wave rises a little bit in height in shallow water, and then it starts to feel the bottom, so it breaks. So it starts reducing in height as it comes down. And in this case, the wave height at the structure is probably 1 to 1.3 metres. So the wave height by the time it hits the structure is about 1.3, but we started with 6 metres offshore. The other thing that does happen though, this is our water level, and we might start with about 1.4 metres offshore, but this is the wave setup process comes in. So as the wave loses height, it gives a bit of its energy into the water level, so the water actually rises near shore, and that's certainly one of the biggest processes in tropical, if you're ever doing any applications on tropical atolls, coral atoll type situations where the wave setup, even though they've got a small tide range, the wave setup brings the water level up over the top of the reef, and then the waves come straight over the top of the reef. So we have a little bit of wave setup in here which brings our water level up quite a bit higher than what we were out in the deep ocean. So that's how we get our wave height at the structure. That's a mid-level way of doing it. There's even more sophisticated ways, but that's a 1D numerical model. Once we've got a wave height at the structure, we need to work out whether our containers are stable. So we came up with I'll show you some examples soon. We did a fairly big physical modelling program of geocontainer stability. And just like a rock structure, we try and work out, obviously you can allow a certain amount of damage without considering it to be failure. And with rock structures, the generally accepted coastal engineering standard is you're allowed to have up to 5% of rocks move from where they started, and that's still considered no damage. So because there's a lot of flexibility in rock structures, 5% of the rocks can move from where they started, and it's still considered a no damage criteria in inverted commas. For geotextile containers, there's still flexibility compared with a rigid, solid, say a brick wall. There's flexibility, but probably not as much as a rock rubble structure. So we came up with, through the physical modelling, we came up with some criteria when the structure was either no damage, initial, or failure. And it's basically a % of the number of units that move. So we came up with this table for both single layer structures or double layer. And we would always recommend, which I'll show later, to construct them with double layer, so two thickness structure. Obviously no damage is no units moving. Initial damage for the geotextile structures is up to 2% of units can move. So if you get up to 2% of units moving, the structure still remains very coherent. With rock structures, that's generally considered to be 5% though. So it is a lower threshold than rock structures. Intermediate damage, where the structure looks pretty damaged, but it's not, it still fulfills its function, between 2 and 15% damage. And we found that for a double layer structure, once you had 15% of the units move, the structure effectively fails. Once you go to single layer, because there's not as much resilience in it, once 10% of the units get moved from their initial position, the structures usually fail. So that's the sort of damage criteria that I'll show from the curves in a moment. So for that initial damage criteria, which is less than 2% of the units moving, what we did is came up with some curves. This is published in in the Australasian Coast and Ports Conference 2009. There's a conference paper that this is into, so it's out on the public record. We came up with some design curves for revetments made of geotextile structures. These are the two common sizes that Geofabrics Australasia make, the Elco rock product. This is a 0.75 cubic metre product, and this is a 2.5 cubic metre product. So how this graph works, this is the significant wave height at the structure. So this is effectively the waves that are reaching the structure and potentially breaking on the structure. The graph goes from 0.5 metre up to 2 metres here. So this is the wave height at the structure. The axis along the bottom is the wave period. If you're into coastal engineering, the TP value, but that's, if you're not into coastal engineering, wave period is basically the time in seconds between the individual waves. So higher energy ocean swell has a longer wave period. So 5-second waves are what you might see in a reasonably sheltered waterway, say on the shores of Moreton Bay, where you've got a 5-kilometre fetch, 5 kilometres of water before you reach land on the other side. So that's the sort of waves you'll get inside, say, Moreton Bay, 5-second waves. A big long-distance swell, say, generated down in the Southern Ocean, typically is up around about 15 seconds, can be 20 in some circumstances. So most of the open coast of southeast Queensland, New South Wales were generally in the 10 to 15 second range for wave period, but an enclosed water body more like 5. So these design curves, what this is saying, the longer wave period waves are travelling faster, they have more energy. So that's why these curves fall down for longer wave periods. So what this is saying is that a 5-second wave, 0.75 cubic metre container will not be damaged for about a 1.5 metre wave hitting the structure. It drops to about 1.3 as we go to a 10-second wave, and it drops to about 1.1 metre as we go to a 15-second wave. So that's the sort of waves that can actually repetitively hit the structure without damaging it. If we go to the 2.5 cubic metre units, they can withstand a wave between about 2 metres and 1.5 metres. So even though we go for a much bigger volume container, we don't get a substantial increase in wave height, but we do get an incremental increase in wave height. So this is what the damage actually looks like in a structure. When we exceed the design threshold for the structure, this is what it actually looks like. So I've got a video of this later, but just to show an extract from the video, we have a structure, revetment built up here like this, and it's non-overtopped in this case. So this is only the damage to the face of it, not to the crest. We run waves on it, and if we run waves big enough to exceed the capacity of these units, this is what actually happens. So this is how they traditionally fail if they're not overtopped. The other failure is if they're actually overtopped, but eventually you exceed the design wave height, units start getting plucked out of the face of the wall. So on the downrush of the waves, they normally get plucked out of the face of the wall and they start falling down onto the sand bed in front of the structure. So that's probably the step that most people are fairly obsessed with, is what design wave height they will withstand, but there's certainly a lot more than that. I mentioned that failure mechanism for non-overtop structures, but you need to work out whether it is going to overtop or not. So step 15 is consider wave run-up and overtopping, and that determines, that's a way of seeing what crest level you actually need. Nevertheless, you may have to allow it to overtop because you may find that the crest you need is 8 metres AHD and there's a house at 5 behind it, and They don't want their view lost. So sometimes you may have to design for overtopping, but at least know whether you're designing for overtopping. If it is an overtop structure, I've got a photo of it, you'll see the most common damage mechanism is the crest bags are damaged. So you need to think about some clever ways of designing the crest. So when you know what the run-up level is, optimise the crest within the project constraints. So overtop structures may suffer a different damage mechanism to structures which are not overtopped, but it's just a real-world reality. Sometimes you need to allow them to overtop. Once you've worked out a crest level, it's a matter of optimising the footing level, what the toe level of your structure is, and the number of layers. I said earlier, we would always recommend 2 units, but I've got some examples, a two-layer thickness structure, but sometimes the resources aren't there and people go for single-layer structures. But at least make a conscious decision if you are going to go for a single-layer structure, why you're going to do that. If you found the structure too high, I mentioned the toe level or the footing level. If you found the structure too high, if it's put too high, obviously if you put your structure at about +2 AHD and the storm comes, scours it to -1, your whole structure is probably going to fall into a hole as well. So be careful about not undermining it. Even if your toe is at -1, which is the general rule of thumb, there are some good toe details that Geofabrics Australasia have to allow for scour. If it happens to scour to -2 or a little bit more than you designed for, you can still have a good toe design that allows it to collapse in the hole and not collapse your whole structure. So the run-up example I gave, or the example of how to calculate the run-up, the 2009 Coast and Ports Conference paper has this plot in it as well. What it shows is if you have a 1 metre wave hitting your structure, how far up the structure will that wave run? Realising that the geotextiles they're not as smooth as a smooth piece of concrete, but they're not as rough as a rock rubble or rock boulder structure. So the run-up is somewhere in between a boulder structure and a smooth piece of concrete or a smooth piece of glass. So it is higher than rock structures. So again, wave run-up increases with wave periods, so we do it for a 5-second wave and a 15-second wave, 5, 10 and 15. As you'd expect, the run-up gets higher with the longer wave periods. So what we found, 10 seconds is probably the most common design parameter for the open coast. This is actually what's called non-dimensional run-up. So 2 means that the run-up is twice the wave height. So for 10-second waves, the run-up is between 2.5, it's around about 2.5 times the wave hitting the structure. So if you get a 1 metre wave hitting the structure, the run-up is about another 2.5 metres above that. So that's just a basic graph to get some idea of what sort of run-up you're going to get. If the run-up exceeds the crest, here's an example of what actually does happen unless you do a lot of careful crest detailing. So this is an example of a geotextile structure that the crest was quite low. It was around about 2 to 3 metres AHD, the crest, and possibly 4 in places, but mostly 2 to 3 metres AHD. It should be around about 5 to withstand run-up, probably 5 and even 6 is what it needs to be to withstand run-up. So the run-up during this storm went right over the top of the wall. So what happened? The run-up went over the top of the wall, so the dune behind the wall started to erode, and so it eroded down, and so then it started digging a hole behind the structure, so then the bags start falling into the hole behind the structure, and then the crest lowers a bit more, so then some of those bags just peel off and fall into the hole. So that's an example of the damage mechanism if you do allow overtopping. There are potentially some fairly clever ways of trying to strengthen the crest, or you certainly need to consider how to strengthen the crest if you were going to design for overtopping. So I've got an example of trying to put together all of those steps that I've shown into a case study. We use offshore waves. We use offshore waves around about 6 metres. The example I showed you earlier of the waves transforming to the shore. When we put that together for that given example I showed, we get about a 1.1 metre wave at the structure. If we use the 0.75 cubic metre containers, 1 to 1.5 slope, the design curves show they're acceptable for a wave height up to about 1.3 metres. So those containers are stable for that given location. If we look at wave setup and overtopping for that particular case, even though we start with about a 1.5 metre offshore water level, we get wave setup brings our water level up to about 2.2 metres AHD. So our nearshore water level is about 2.2 metres AHD, and then we've also got wave run up on top of that. So our 1.1 metre wave gets multiplied by about 2.7, and we add that to our water level, and we come up that the crest of that structure needs to be about 5.25 metres AHD to stop run up. So for that case, we would suggest a 5.5 metre AHD crest level. The examples of the overtop structures, this would apply to that example you saw of the damaged structure, and they had a crest of between 2 and 3 metres AHD. So that's why it's substantially overtopped. It needs to be about 5.5, and they've got it at 2 to 3 metres. But there are other project constraints that kept it down at that low level. So that's an example of setting the crest level and setting the toe level and the container size. If you are going to have an overtop structure, you've got to design it for overtopping. So you may need some additional crest strengthening of the structure so that the bags aren't dislodged, or if they're dislodged, they don't just fall into a hole and the whole structure collapses. Also, probably at this stage in the project, think about where you're going to get the filling sand from. Nearly always it's from the beach nearby where the structure's being built. If it's an emergency situation with a large amount of storm erosion, that may not always be feasible. So think about sand sources which may have to revert to a nearby estuary or bought in commercial sand from a quarry. There's a bit of a talk about fabric selection. There's a step on fabric selection as well. Warren's talk will address that a bit more than I do, but certainly think about the different grades of fabric, because obviously there's better grades of fabric that you spend more money on, or very cheap grades of fabric that are probably not going to last more than a few months out in the weather. Also investigate the available machinery for constructing the works. Again, if you're anywhere on the mainland of Australia between Noosa and Hobart, or pretty much anywhere on mainland Australian coast, there's going to be available machinery, particularly if you're near any capital cities or major regional centres. If you're proposing to do something like this on Lord Howe Island or King Island or Pitcairn Island, certainly there's not going to necessarily be the machinery you want there, which may influence the container size, because the bigger containers need different machinery and bigger machinery and specialised plant to construct them. So think about what machinery you might have to build it, and that may push it down to the 0.75 cubic metre containers versus the 2.5s. Now's the time, if you haven't already established a project budget, it would be time to. I'd suggest you should just be revising your project budget by now, but in some circumstances, if you have no idea, you now do have an idea once you've got to this level in the project. So you can estimate it fairly accurately by this stage in the project. And subject to your budget and a range of other inputs, it's time to maybe review and refine the design parameters, and it may require a complete reiteration of that design process. For example, maybe to allow for overtopping, or to cut back to a single layer structure, or to think about a different container size as well. At this step, reconsider the need for physical modelling. If the consequences of failure are large or the uncertainty is high, project-specific physical modelling is still a recommended method, not just for geotextile structures. All the standard coastal engineering textbooks have design curves for rock structures, but they all recommend that's just the desktop method, and if the consequences of failure are high, physical modelling is a recommended method by all the major world authorities in coastal engineering. So if it's a big project with a lot at risk, project-specific physical modelling is still the preferred way at this stage for your detailed design. I've just got an example here of a video showing physical modelling of how we got the design curves for these structures. So this is flume modelling. It's sped up. It's a different time scale to what you actually see. Right, so these are waves. So this is about a 1 in 10 scale of model testing. And you'll see, if you look, damage is starting to initiate around here. You can see we have lost a container down the bottom there as well. So nearly all the damage occurs within the waterline. So obviously you don't get damage up here, but basically above and below the mean sea level. This is equivalent to about it's equivalent to 1 to 2 hours of real world testing this. And it's, even the test program speeds up the time, and this is just a little excerpt as well. But you can see we start getting damage. It's a double layer structure, so the bottom layer is still completely intact though. You see where the damage has occurred, and we've started losing bags out of the face of it. And realise the aim of physical modelling is we have to test things to destruction or damage, otherwise we never know what the threshold is that the damage occurs. So that was an example of physical modelling, and that's how we generated the design curves for these structures, and I've got some examples of that later. A few more design steps, not too many to go. Detailed design of the structure, which is document the adopted design, which may be suitable for tendering or for construction. So come up with some reasonably good documented design, and that includes fabric selection as well. It may also involve input from a geotechnical engineer, because you're ultimately designing a retaining wall structure is what it is. And coastal engineers generally, the coastal engineering is all about the stability of the containers, but the stability of the wall itself in a saturated sand environment may require input from a geotechnical engineer as well. Document the process, assuming that's all happened and you've commenced building your structure, document the process of construction through photos and survey records. Because these are often temporary structures and the life of them well exceeds what they were designed for, and they're often in contentious coastal areas where there's difficult decisions as to what the long-term strategy is. Probably like any coastal structure, it can often end in litigation, and I have been involved in several cases where there's a big argument about what was actually built, because it was built 10 years ago, no proper records were kept, and then there's a big argument about what was built. So the better you document it, the more watertight it is if something goes wrong down the track, or if it's damaged and the damage exceeds what it was designed for example, versus if it's damaged, versus whether there's an argument about whether it wasn't built to design, or whether it's simply that the design exceeded what it was designed, the conditions exceeded what it was designed for. So similarly, prepare as-built drawings. I'd always recommend that. They assist with documentation and with future monitoring as well. So once it is built, monitor the structure, I would always suggest, or develop a monitoring program. It can include visual inspections, surveys of the crest periodically, or documentation. The monitoring program should include what tasks you're going to do to monitor it and how often you should do them, and that's really part of the design. Some of the standard coastal engineering references, like Coastal Engineering Manual from the USA, they do say you can make a structure that your procedure is no monitoring at all. As long as you accept you're going to have no monitoring, or just purely reactive monitoring, where if someone rings up and says it's damaged, then you do something, that's acceptable if it's been a well thought out decision. That can be acceptable in some circumstances if the risk is low, but at least work out what monitoring you intend to have. And if you're not going to monitor it at all, make that a conscious decision rather than just something that happens, and then when it's damaged, there becomes a blame game as to how that damage occurred. So maintain or repair the structure as required, and that can be preventatively or can be reactively, simply reacting to damage. Warren will talk about some of the damage mechanisms that occur, and probably the most common is accidental damage through debris or boat anchors, or deliberate damage through vandalism. There are standard patch mechanisms available to deal with that sort of damage.